Welcome to this explainer. Okay, so let's just completely shatter this idea we all grew up with. You know, the one where math is just this rigid, finished rulebook of boring memorization? Where it's all about just flipping to the back of the textbook to find the exact right answer? Today we're actually heading to the absolute frontier of human logic. We're going to look at the deep cracks in the foundation of numbers, these wild, unsolvable puzzles, and honestly, the beautiful flaws that make math this living, breathing, chaotic landscape.
Right, so to get there, we got to start with an earth-shattering realization that fundamentally broke mathematics in the 20th century. For thousands of years, I mean, literally going all the way back to Euclid, math was the ultimate bedrock of absolute truth. But as mathematicians kept digging deeper and deeper into the basic foundations of logic, they hit something incredibly unsettling. They found out there's a hole at the very bottom of math, a fundamental flaw that implies, well, we might never actually be able to know everything with 100% certainty.
Now I know what you're thinking. That sounds absolutely terrifying, right? Does this mean we can never know anything for sure? Well, surprise! This question actually unlocks a wild universe of unsolved mysteries and impossible paradoxes. It turns out that this huge limitation isn't a dead end at all. It's actually a massive engine for discovery. And to really wrap our heads around why, we need to look at one of the most dramatic intellectual showdowns in all of history.
You can see this tension perfectly summed up in the epic clash between David Hilbert and Kurt Gödel. So picture this, it's 1930. Hilbert, who's basically the undisputed king of mathematics at the time, declares that math absolutely must be perfectly complete. His famous battle cry was, "We must know, we will know." But then literally the very next day, this 24-year-old kid, a logician named Kurt Gödel, drops a total bombshell, his incompleteness theorem. He mathematically proved that in any basic system of arithmetic, there are always going to be true statements that are mathematically impossible to prove. Boom! The bedrock of math was officially incomplete. Truth and provability? Yeah, it turns out they are not the same thing at all.
Which brings us to Act 1, Simple but Impossible Problems. Let's get into it.
So if the very bedrock of math is incomplete, it means we can find seemingly impossible mysteries hanging out right in our own backyard, using just basic grade school arithmetic. Take the Collatz conjecture. People legitimately call this the most dangerous problem in math. The legendary Paul Erdos actually warned young mathematicians to just stay away from it. It's so simple. Pick any number. If it's odd, multiply it by 3 and add 1. If it's even, just divide by 2. Do that, and you'll create this chaotic, bouncing string of what mathematicians call hailstone numbers. They bounce wildly up and down, but eventually they seemingly always crash back down to the number 1. But here's the crazy part. No mathematician alive can fully explain why. Nobody can prove it works for every single number. It is completely, utterly unsolved.
Or, hey, consider the twin prime conjecture. So prime numbers, they're the building blocks of math, right? Numbers only divisible by 1 and themselves. Well, twin primes are pairs separated by just 2 spaces, like 11 and 13 or 29 and 31. Now, Euclid wondered over 2 millennia ago if these pairs just keep popping up infinitely as you count higher and higher. 2,000 years later, we literally still don't have an answer, and because of Gödel's whole incompleteness thing we just talked about, it is entirely possible that this is one of those true statements that just straight up has no proof.
All right, moving right along to Act 2, the deep architecture.
Now, things get really wild when we move from simple arithmetic to the deep, hidden architecture of the universe. Specifically, how a 19th century genius tried to tame the totally chaotic distribution of those prime numbers. Enter Bernhard Riemann. He essentially took some older work by Leonhard Euler and completely folded it into a 3D landscape using imaginary numbers. You know, numbers involving the square root of -1. He hypothesized that if you look at this mind-bending new Riemann zeta function, the spots where the function equals 0, specifically the non-trivial zeros, exactly map out the locations of prime numbers. It's almost like a fundamental wave frequency for primes. If he's right, it would perfectly predict them. This is the Riemann hypothesis, and it is arguably the single greatest unsolved problem in math today.
To put that into perspective, wrap your head around this massive number, 10 trillion. A giant computing project actually went in and brute force checked the first 10 trillion of these zeros to see if they perfectly line up on Riemann's critical line. And guess what? They did. 10 trillion times without a single error. But, and this is the beautiful, hair-pulling frustration of math, brute force computation is completely useless for actually proving the hypothesis. Why? Because numbers go to infinity. You can't just check them all. You need a rigorous logical proof. And so far, nobody on Earth has one.
Okay, let's step into Act 3, topology and bending the rules.
So if arithmetic and prime numbers are hiding these deep, uncrackable secrets, what happens when we look at physical geometry? Check out this question, originally posed by Otto Toeplitz way back in 1911. It's called the inscribed square problem. The question is surprisingly simple. If you draw any continuous closed loop, literally just a random squiggle that ends exactly where it starts, can you always find 4 points on that loop that form a perfect square? Now, for nice, smooth curves, the answer is yes. But for rough, jagged, crazy fractal curves, it's another massive unsolved mystery.
To solve totally bizarre puzzles like this, mathematicians turn to a fascinating field called topology. Now, a lot of folks think topology is just, recreational math about weird rubber sheet shapes. But actually, no, it's a super rigorous tool for logical deduction. It's essentially a game of understanding exactly what is or isn't possible when you stretch, bend, and continuously map objects.
And this is where topology basically becomes a superpower. When mathematicians were trying to prove that you could at least find a rectangle in any continuous loop, they mapped out all the possible unordered pairs of points on that loop. And when they visualized that abstract data, it naturally folded itself into a Mobius strip. You know, that crazy shape with only one side? Understanding exactly how this theoretical shape behaves was the literal key they needed to prove that these loops absolutely must contain rectangles. It's like a giant multi-dimensional puzzle.
And if you take that logic just one step further, you get the Klein bottle. See, when you glue the edges of two Mobius strips together, you create a four-dimensional shape that physically cannot exist in our 3D world without intersecting itself. It's impossible. But mathematicians actually use the absolute physical impossibilities of these shapes in 3D space as the strict constraints they need to fuel their logical proofs. The impossibility itself is the proof. How cool is that?
Which perfectly sets up our final section. Conclusion: the power of not knowing.
So, what does this all mean for us? How does this abstract stuff build into something that impacts your daily life? Well, we've seen how math is jam-packed with unprovable truths, unsolvable conjectures, and impossible geometry. But here's the kicker. This foundational flaw, this total inability to prove everything, actually gave birth to the modern world. Looking at this timeline, over just a few short decades, absolute mathematical certainty just completely collapsed. Cantor gave us different sizes of infinity, Russell broke set theory with self-reference, Gödel proved math is incomplete, and the whole shebang culminated with Alan Turing in 1936 when he tried to answer David Hilbert's final lingering question, is math decidable? To figure that out, Turing imagined a theoretical computing machine. But in doing so, he realized that just like math is undecidable, computing has a fundamental limit too. It's called the halting problem. Basically, this means there is absolutely no possible algorithm that can look at a computer program and perfectly determine if it'll eventually stop running, or if it's just going to get stuck in an infinite loop forever and ever.
And because Turing's theoretical machine is the foundation for all computing, any complex system that is Turing complete shares this exact same flaw. It is literally everywhere. We're talking Conway's game of life, the spectral gaps in quantum physics, massive airline ticketing systems, and, believe it or not, even the card game Magic the Gathering. Because all these massively diverse systems process complex logic, they share the exact same unanswerable paradoxes. You just cannot mathematically predict their ultimate outcomes.
But here, right here, is the ultimate twist. And honestly, the reason we should celebrate all of this. To prove that math was fundamentally undecidable, Alan Turing was forced to design that theoretical machine to process the logic. And that theoretical Turing machine, it became the direct blueprint for the very first electronic computers. I'm talking about the phone in your pocket, the screen you're staring at right now, the digital infrastructure of the entire modern world. It all exists purely because math was broken. The flaw wasn't a bug, it was actually a feature. So, as we wrap up this explainer, I want to leave you with this final thought to really chew on. If our absolute greatest technologies in the entire digital age were born from math's ultimate failures, what world-changing inventions are waiting inside the questions we can't answer today? The hole at the bottom of math isn't a failure at all. It's the ultimate engine of discovery, constantly pushing us to the very edge of human knowledge. Thanks so much for joining me today. Keep asking those impossible questions, and I'll catch you